Hi, welcome to the topic of multiple integrals. In this topic, we are going to learn about double integrals and triple integrals. In double integral, we will explore integrals in Cartesian coordinate system and polar system. Whereas for triple integrals, we will look into the integrals in Cartesian, cylindrical, and spherical system. Let us recall the integration in two-dimensional system. When we want to find the area below the curve fx, we used rectangles to approximate it. The greater number of rectangles, the more accurate is the approximation. And the approximation turns into integration when the number of rectangles is approaching infinity. We are using the same concept for double integral. If we want to find the volume below a surface fxy bounded by four planes x equals to a, x equals to b, y equals to c, and y equals to d, the approximation can be done using the volumes of cuboid, which the volume is taking the height fxi yj to multiply with the area of the base delta aij, where I starts from 1 to m and j starts from 1 to n. So in total, we have m times n number of cuboids. The greater number of cuboids, the smaller size of cuboids, and the approximation become more accurate. When m and n go to infinity, okay, the approximation turns into double integral. When they go to infinity, it turns to double integral. Take note that the sign of the integration originates from the s of sum. The sign here originates from s of sum. That means we are actually finding the summation of the volume with m times n number of cuboids when we perform the double integral to the surface fxy. Let us look at the notation of double integral. You may need to remember the names of each element in the notation. The double integral starts with the integral signs. The function inside is called as integrand, and dA, which can be dx dy or dy dx, is called as differential. When the limits of integration are yet to set, or the order is yet to set, the symbol r will be placed below the double integral sign to represent the region, and the differential is written as dA. The region here refers to the projection of the solid on xy plane, or the base of the solid. If the order of integration is determined, then the limits need to be put in. For example, if the differentials are arranged in the order of dy dx, then the inner integral sign and its limit y equals to c and y equals to d for the variable y, whereas the outer integral sign and its limit x equals to a and x equals to b are for variable x. According to Fubini's theorem in the first form, it says that the double integral of different order gives the same result. They are the same. This is only true when the region is a rectangle. What is the difference between the first line and the second line here? Perhaps the following graph can give some insights. If we choose the order dA equals to dx dy, okay, dA equals to dx dy, it means we find the area of the cross section AY. Okay, this is the AY. We find the area of the cross section AY, which is the integration of fxy with respect to x from x equals to a to x equals to b first. Then we find the volume of the solid by integrating the area AY with respect to y from y equals to c to y equals to d. We use the similar concept for dy dx. In this graph, we want to find the volume of the solid bounded by the upper surface fxy. The planes x equals to -1, x equals to 3, y equals to -2, and y equals to 3. So if we look at these inequalities, we'll be able to see the region. It will be easier if we just refer to the projection of the solid at the xy plane to find the limits. You can see here we have a rectangle. So after finding the limits, we may start to integrate the function. Please keep in mind that the integration is done from inside out. Okay? Similar concept with partial derivatives. When we integrate a function of several variables with respect to x, we treat other variables as constants. Let us go through one example for better understanding. Calculate the double integral of fxy if fxy is equals to 100 minus 6x squared y, and it is bounded by the region, that is the region R, which is defined by x falls between 0 and 2 and y is between -1 and 1. Now, if we take dA equals to dx dy, we get this integral. Then we start to integrate the function with respect to x first, and we will get, remember, we treat other variable as constant, so we have 100x minus 6x cubed y over 3, where x is from 0 to 2. Don't forget the differential dy. Okay, we can simplify this 3 and 6, and we get 2x cubed y. Okay, and then we substitute the upper and lower limit into the x. We get 200 minus 2 cubed is 8. 8 by 2 is 16. So 16y, this is from the upper limit, minus the expression with the lower limit, that is 0. So we can continue to integrate now, and we get 200y minus 8y squared. The 0 you integrate, you still get 0. So y is from -1 to 1. Then we continue with our steps, that is to substitute the upper limit into the y minus the expression with the lower limit. We get 200 minus 8. This is from the upper limit, and from the lower limit it is -200 minus 8. So 200 minus -200, we get 400. -8 minus -8, you get 0. So this one we will get 400. Okay, so that's how we do the integration. Now, why don't you try this question again with another order, dy dx. dA equals to dy dx. The answer must be the same. So that is all for this video. Thank you for watching. We will learn more in the next topic when the region is not just rectangle. See you there.